Electric field or electric field intensity. Electric field intensity at any point due to the source charge is defined as the force experienced per unit positive charge at that point. It is denoted by E. E is equal to F by Q. Electric field is a vector quantity. The unit of electric field is Newton per Coulomb or Volt per meter. Electric field due to a point charge. Let point charge Q is kept at origin. We require electric field at point P due to the charge capital Q. The distance of point P from Q is R. To find the electric field, test charge Q0 is placed at the point P. Force between Q and Q0 is given by equation F is equal to K Q0 divided by R square into R cap. Therefore, F divided by Q0 is equal to K Q by R square into R cap. But F by Q is electric field or electric intensity. So E vector is equal to KQ by R square into R cap. The magnitude of electric field is given by equation E is equal to KQ by R square. Therefore, electric field due to a point charge is proportional to 1 over R square. Electric field lines and its properties. Definition of electric field line. An electric field line is a curve drawn in such a way that tangent to it at each point is in the direction of electric field at that point. Properties of electric field lines. First, field lines start from positive charge and end at negative charge. Electric field lines start from positive charge and end at negative charge. Outward from positive charge, inward for negative charge. Second, in a charge-free region, electric field lines can be taken to be continuous curve without any breaks. Third, two field lines can never cross each other. If two field lines cross each other, then the tangents drawn to this field line shows that at the point of intersection, the electric fields are in different direction. At single point, there are two directions of electric field. This is not possible. That is why two field lines never cross each other. Fourth, electrostatic field lines do not form any closed loop. Fifth, in any region, if electric field lines are closer, say here region A, then the electric field is more there, and if the electric field lines are far, then the electric field is less there. Here EA is greater than EB. Sixth, electric field lines are perpendicular to the surface of charged conductor. 7. If the electric field lines are parallel to each other and they are at equidistance, then this is known as the uniform electric field. Here if point A is there and point B is there, then we can say that EA is equal to EB. Electric dipole. An electric dipole is a pair of equal and opposite charges separated by some distance. Let two equal and opposite charges are plus Q and minus Q. If they are separated by distance 2a, then this pair is known as the electric dipole. The product of magnitude of any one charge and the distance between two charges is called the dipole moment. Dipole or dipole moment is the vector quantity. The direction of it is from negative charge to positive charge. The unit of electric dipole moment is Coulomb into meter. The total charge on dipole is 0, but electric field of dipole is not 0 because two charges are separated by some distance. Electric field on the axis of an dipole. And dipole is given in the diagram. we required electric field at point P on the axis of dipole, electric field at point P due to the positive charge toward the left side, electric field at point P due to the negative charge is toward the right side, dipole moment from negative to positive, so it is in the left direction. The distance of P from the midpoint of dipole is R. Now, electric field at point P due to the positive charge, EQ vector is equal to K Q R minus A square. Now here electric field due to the positive charge and dipole moment are in the same direction, so we can write here P cap. Electric field due to the negative charge at point P is given by KQ R plus A square. Here electric field and dipole moment are in opposite direction, so minus P cap, so it is minus KQ by R plus A square into P cap. Total electric field at point P is given by E plus Q plus E minus Q. Put the values, substitute the values of E plus Q and E minus Q. K Q divided by R minus A square P cap minus K Q R plus A square P cap. K, Q and P cap are common, so it is 1 over R minus A square minus 1 over R plus A square into P cap. Take the LCM KQ. Here LCM is R minus A square R plus A square. Here it will be R plus A square, that means R square plus 2AR plus A square. Here R minus A square and negative sign is in between, so it is minus R square plus 2AR minus A square into P cap. So it is K Q. R square and negative R square are cancel out. A square and negative A square are cancel out. 2AR plus 2AR, so it is 4AR. R minus A, R plus A, so it is R square minus A square, and here whole square P cap. Now here we can write like this: K Q 2A R square minus A square raised to 2 into P cap. But Q into 2A is dipole moment, so electric field is given by the like this: 2 K P R divided by R square minus A square raised to 2 into P cap. Here electric field and dipole moment are in the same direction. Now if R is much more greater than A, then R square minus A square may be written as R square. So E is equal to 2KPR R square raised to 2 into P cap. Here R raised to 4, 1 R is cancelled out. So E vector is equal to 2Kp by R cube into P cap. So we can say that electric field on the axis of a dipole is proportional to 1 over R cube. Electric field at an equatorial point of dipole. Let electric field is required at distance R on the equatorial line of dipole. Here this distance is A, this distance is R. So AP and PB both distances are R square plus A square raised to 1/2. Now electric field at point A due to the positive charge is in this direction. This is E plus Q. Electric field due to the negative charge at point P is in this direction. This electric field is E minus Q. If this angle is theta, then this angle is also theta. So we will have two components of E plus Q cos theta and E plus Q sin theta. Similarly, E minus Q has also two components, E minus Q cos theta, and the perpendicular component is E minus Q sin theta. If this point is D, then for triangle APD, cos theta is AD divided by AP. So cos theta is equal to A divided by R square plus A square raised to 1/2. Now, magnitude of electric field due to the positive charge is given by KQ divided by AP square. So it is KQ divided by R square plus A square. Similarly, electric field, magnitude of electric field due to the negative charge is KQ divided by PB square. So it is KQ divided by R square plus A square. Now these two are similar. That means the components E plus Q sin theta and E minus Q sin theta are in same magnitude and in opposite direction. So these two components cancel out each other. You can see here E plus Q and E minus Q cos theta are in same direction. That means the total electric field is due to these two components. Now say E plus Q and E minus Q as EQ, as both are same. So total electric field at point P is given by EQ cos theta plus EQ cos theta. So it will be 2EQ cos theta. Now see here, dipole moment is from negative to positive. So here dipole moment is from B to A. This is dipole moment direction, and our electric field is in this direction. These two are in opposite direction. So here we can write minus P cap. So electric field at point P is given by 2. EQ is KQ divided by R square plus A square. Cos theta is A divided by R square plus A square raised to 1/2 into P cap. So it will be like this, minus K Q into 2A divided by R square plus A square. Here 1 power, here 1/2 power. So total power is 3/2. But Q into 2A is P. So E is equal to minus KP divided by R square plus A square raised to 3/2 into P cap. Here negative sign indicates that electric field and dipole moment are in the opposite direction. Now if R is much more greater than A, then R square plus A square is written as R square. So our equation will be minus KP divided by R square raised to 3/2 into P cap. That means E is equal to minus KP divided by, here 2 cancel out, so R cube into P cap. So electric field on the equatorial point of dipole is proportional to 1 over R cube.